Hello everyone, and welcome to this session about lighting your big data fire with Spark on AWS. My name is Russell Nash. I'm a solutions architect with AWS focusing on the data space, and I'm delighted to be spending the next little while with you talking about Spark, talking about why it's become so popular so quickly, what are some of the use cases that our customers are using it for, and also the best practices for using it on AWS. So our agenda today is we're going to take a little bit of a step back at first, and we're going to look at the Hadoop family tree. And we're going to do that because that's going to make it very obvious where Spark fits into the big data landscape, so that we can then see what it's actually replacing and what kind of technologies it's complementary with. We're then going to delve a little bit deeper into Spark itself and look at all the goodies that come with it. And then we're going to look at Amazon EMR. So EMR is our managed Hadoop service, and we're going to look at some of the characteristics of EMR and why that works so nicely with Spark. And then we're going to look at marriage, and we're going to look at the marriage of EMR with Spark and talk about why that's a good thing. So let's kick off and look at the family tree. So if we take a little bit of a step back, there was a time when, before we had distributed computing became the norm, there was a time when we would try and do as much processing as we could on a single machine, and we were really limited by the resources on that machine. So we would obviously have a certain amount of disk on that machine and a certain amount of compute and memory that we had to work with. And so as our data set started to grow and some of the things that we wanted to do became a little bit more complex, we would look at making that machine larger and trying to take advantage of bigger instance sizes, more CPUs, more disk, etc. But obviously there's a limit to how far you can push that, how far you can vertically scale. And as Grace Hopper said, and she said this back in the 60s, so she was well ahead of her time here, she said that in pioneer days they used oxen for heavy pulling, and when one ox couldn't budge a log, they didn't try to grow a bigger ox. And she goes on to say after that really we should be looking at a network of computers rather than trying to do everything on a single machine. So as I said, she was well ahead of her time because she'd said that over 50 years ago. But basically we followed her advice, and if you look at what we then tried to do, we then tried to grow beyond a single machine, and we said, okay, let's use a cluster of machines. Why don't we use the disk and the CPU and the memory on a number of machines, and this gets us past the problem of scaling on one machine, and obviously as we need to grow we can add more machines to this cluster. Now in theory that sounds fantastic, but there's a couple of issues, a couple of problems that we really need to get around, and one of them is that you need something to really manage this whole process, because if you're trying to utilize all the disk on those machines, you need something that's actually going to coordinate where does each piece of data live in this whole cluster, and how does it actually move between the different bits of compute that we've got on the different machines. And so that was really why Hadoop was born, to try and solve this problem, to really give us a framework to take the complexity out of this for us, so that we could actually just focus on writing applications rather than the minutiae of actually managing the data and the compute, and basically just get to it writing things. So let's have a little look at Hadoop from the ground up. So originally, obviously, at the bottom of the stack, you've got some infrastructure. Now that might be physical infrastructure if you're doing this on premise, or it might be virtual machines. So it would be EC2 if you're running this in AWS. And then on top of that, we then layered HDFS. So this was our data layer. So HDFS is Hadoop's distributed file system. And this gave us the abstraction that we were looking for across the disk on the machines in our cluster, so that we're not having to write directly to each machine. We can basically just pass the data to HDFS, and it will take care of distributing the data for us. The process layer that was originally designed for Hadoop was called MapReduce, and MapReduce was kind of the first of its ilk to really do the magic of allowing us to write to this distributed framework. Now the framework itself that sits across this whole thing and coordinates everything was called Hadoop, named after one of the original writers of Hadoop, Doug Cutting, right, named after his son's toy elephant. And that became the new distributed paradigm. Now, as with anything that we introduce in the IT industry, that was fine for a certain amount of time, and then people said, hey, we want to not write to MapReduce directly because it's fairly low level. We're writing in low level languages like Java, which is fine if you're a Java developer, but if I'm a slightly more business facing user, I might want to use something that's a bit more business friendly, like say SQL, for example. So a couple of the first applications that were written, the first was Hive, which is a SQL-like layer across Hadoop and MapReduce, which allows people to write in a SQL-like language, and that would then be translated into MapReduce so that you could get your result sets. The other early one was Pig, and Pig provides you with a language that allows you to transform data. And so that was used very extensively as well, and still is to this day. I learned the other day what the reason that it's called Pig actually is because it eats anything. So you can throw pretty much anything at it, and it will deal with it. So this was obviously fine as we went along, and again, you know, people were using this quite happily, but wanted to push it further. So as Hadoop evolved and we got to Hadoop 2, there was an extra layer that was added in here to try and make things a little bit more flexible. And that layer was called Yarn. So Yarn stands for yet another resource negotiator, and it's basically a resource manager. And what that allowed us to do was to really break the tight association between MapReduce and HDFS, which really then allowed the next kind of stage of evolution for a lot of the Hadoop applications. So what then happened was that MapReduce was then joined by a number of other processing engines that you could then use within this kind of framework. So Tez became very popular. So Tez was quite close to MapReduce in terms of its API, so that people could very easily migrate to Tez, and offered much better performance than MapReduce, and works very seamlessly with some of the applications like Hive and Pig. And then Spark came along as well, and Spark was a slightly more general purpose engine, and we'll look later on at some of the facets of it. But you can see now this Hadoop paradigm really starting to grow in terms of the ecosystem. And then up the top, where we've got our applications, there was an explosion of applications as well. So just a couple of examples, so things like Presto, for example, which were giving people very fast SQL access to the data in HDFS and also in S3, and then Apache HBase, which gives them NoSQL type of functionality. And then Spark brought with it applications like Spark SQL, again a SQL layer, and then Spark Streaming as well, which allowed you to deal with very high velocity data coming into the cluster. Now, one of the interesting things about this is that, so you can see now where Spark kind of fits into the whole ecosystem. And one of the interesting things to say here is that although we're showing Spark running here on Yarn within the Hadoop framework, that's not the only way that you can run Spark. So you can also run it standalone. So you can actually just download it to your laptop and fire it up and start using it. Or you can run it on other resource managers such as Mesos as well. So Yarn's not the only way, but this tends to be the major way that most people use Spark because of the Hadoop framework around it. So that's where Spark fits in. So let's have a little deeper look now into some of the functionality that Spark provides and the reasons why it's become as popular as it has. So anytime you look at any kind of big data press, Spark is always mentioned. It's talked about a lot. There's the Spark conferences now. A lot of organizations have bet their business on Spark. Almost every single big data vendor has announced support for Spark. So it's really starting to become the technology around which the industry is really starting to coalesce. And when you boil it down, there's really two main reasons why Spark is as popular as it is. And essentially, it's because it's fast and rich, which are two facets that are great for anything really. But fantastic for Spark users. So if we look at why it's so fast, there's a couple of reasons for this. So one is that it makes really good use of the memory within the cluster. Now, there's a bit of a misconception that it runs everything entirely in memory. That's not quite true, but it just makes much more efficient use of the memory within your cluster. So as opposed to, say, MapReduce, which tends to write to disk between stages and between processes, which is obviously quite a slow process, Spark doesn't do that. It likes to keep its data into memory as much as possible. The other reason that it's so fast is because there's a lot of optimization in the processing that it does. So it actually looks at the most efficient way to run the job that you've given it and make sure that processes don't block each other if they don't necessarily need to. So two of the main reasons there why Spark is much faster than the original MapReduce. So the other reason that people like Spark and the reason that it continues its dominance is that it's extremely rich in the functionality that you get out of the box. So you've probably seen this type of diagram before. So whenever Spark's talked about it, it's always kind of talked about in this type of way. And so down the bottom, you've got some of the core Spark functionality, the core engine. And then on top of that, you've got a number of modules which are really designed to give you a lot of out-of-the-box functionality that, again, just allow you to focus on the task at hand rather than getting bogged down into the details of kind of writing to some of the lower level languages. So let's step through each of these and talk about what they give you. So if we look at Spark Core for starters, so essentially, if you look at what the core of the engine does, it does all of the distributed processing for you. So it will take care of talking to the data and then abstracting that for use in whatever language you want to use. And so if you're looking just at Spark Core, you can actually write in Python, Java, and Scala, which are three of the most popular languages for use in this space. And that gives you an enormous amount of flexibility and power to then write your applications. The second part of what you get with Spark Core is then obviously access to your distributed data sets. Now, the great thing here is that there's an enormous number of connectors that come with Spark that allow you to access these different data sets. So if you look at some of the connectors that come either out of the box or via third parties, you've got connectors which are specific to particular data formats. So you've got connectors for JSON, Parquet, Avro, and CSV, for example, but also other engines as well, such as HBase, Elasticsearch, Postgres, Redshift, Hive, and then obviously other locations for data as well. So obviously HDFS and also S3 there as well. So tremendously rich in terms of allowing you to pretty much get to any type of data set and then be able to analyze it. Now, similar to what happened with Hadoop and the rise of applications to try and abstract people from some of the lower level workings of some of the engines, we can see that the Spark model is very similar. So one of the first cabs off the rank there, as has become very popular now, is essentially a SQL engine, a SQL layer across Spark. And essentially what that gives you is you're still talking to the same Spark core engine, you're still using the same connectors to reach your data, but instead of writing in low-level languages, you can write in SQL. And SQL, for those of you that were worried a few years ago that that SQL was on the way out, that people were talking about its demise, it is absolutely thriving. And as I said, pretty much any time there's a new technology, often the first user interface that they pop over it is some kind of SQL interface, because it is so well known and so many people know how to drive it. So Spark SQL is a fantastic way to get into Spark without having to learn a new language. So the way that you can use SQL with Spark, so you can use the command line interface, so you can just log in via the command line and write your raw SQL against the data, and that works very well. Or you can take a slightly higher level view, so you can step up and you can use a SQL editor. So Zeppelin is a very popular one that's often used with Spark. Or you can actually, through a JDBC driver, you can actually attach pretty much any BI tool that's out there. And so that's also a popular way is to, again, another layer of abstraction where you're not even writing SQL, you're actually just driving the user interface through the BI tool. So the use cases that we see here are we see a lot of exploratory type of work, trying to understand what's contained in a data set, people trying to kind of get their arms around what's in there, running some type of exploratory SQL. But also we see it used for ETL as well, for extract, transform and load type purposes. So it's very easy within here to actually set up a table that points to a data set, and then set up another table that points to, let's say, an empty file system, and then in the process of copying the data between the tables, you're actually doing the transformation step there. So you may be transforming between different formats, so maybe from JSON to Parquet, for example, or you might actually be transforming the data itself as it moves across into the new table. So Spark SQL, a fantastic way to do transformation as well as exploring your data set through SQL. Now, one of the modules that gets a lot of attention within Spark, and rightly so, is Spark Streaming. So what we're finding with our customer base is that everybody is starting to look at high velocity data, streaming data, whether that's coming from a clickstream, so whether it's people clicking on your website, or whether it's devices that are sending information to you very quickly. You need to be able to not only capture that information, but also then obviously analyze it in flight as well. So what Spark Streaming does for you is it helps you actually to analyze that data as it comes in. So what typically happens is that you have some kind of capture mechanism at the front end. So those of you familiar with AWS might have seen Amazon Kinesis. So this is a streaming engine that allows you to take in a large amount of messages through the front door. Apache Kafka is another very popular open source, very similar in architecture, those two. And what they do is they will capture the data for you and then make it available for you to then consume with some kind of application. And there's a number of ways that you can do that. But one of the most popular ways is to actually have a Spark cluster with Spark Streaming running. So Spark Streaming will actually turn the stream into a number of micro batches. And what those micro batches do is they then allow you to act on those. And so then later on in the pipeline, you'll then use one of the other Spark engines, whether it's Spark SQL or Core Spark, to actually then analyze those micro batches and then push out whatever results you're after. So you can start to see that one of the main attractions of Spark is that it does everything in that one package, so that you're not doing something different after you've done the Spark Streaming. You're staying within the Spark engine and using some of the other facets of it to actually analyze the data. So Spark Streaming, extremely popular amongst a lot of our customers. So one of the other modules is actually Spark R. So R has become an extremely popular language in recent times for more statistical type of analysis. So it gives you a richer set of functionality than SQL does in the kind of statistical space. And one of the limitations of R is that you are often limited by the amount of memory that you have on a particular machine. And so people want to run R on a much larger distributed data set. And so Spark can actually help you do that. And so again, if you look at the the core type of Spark core, talking to the data sets down the bottom, Spark then will allow you to have R on the top that can then access that data. So again, just allowing users who are familiar with Spark, familiar with R, who love R, can actually stay within the Spark framework and analyze their data. Now, another very popular module within Spark is Spark ML. Now, there's actually two machine learning libraries in here. There's one called Spark ML, another one called ML Lib. And they're both involved in allowing you to essentially create machine learning models with your data, and then actually then have you run new data sets through your model and for it to make predictions for you. So if we look at how that works, so if you look at a typical machine learning pipeline inside Spark or outside, the way you typically do it is you take your training data set. So let's say that you're looking to predict a particular variable. So what you do first is you need to train the model so that it actually knows what patterns lead to the particular outcome that you're looking for. So for example, if you were training a model to look for fraudulent credit card transactions, in your training data set you would have a number of transactions with all the different variables, so time, place, merchant, etc., etc. And then you'd also have in that data set whether each of the transactions was actually fraudulent or not. So essentially you're giving the model the answers, which allows it to then work backwards from the answers and look at the actual variables and say, what are the patterns that we're seeing here that leads to a fraudulent outcome? So that's what you typically do, and that typically involves quite a lot of data preparation, because you have to cleanse your data set, you have to make sure that you've got the right variables sitting in the data set that are relevant for the model, etc. So there's a bit of preparation to be done there. And once you've got that, you then typically split that training data two ways. So 70 or 80% of the data actually goes into training the model. So that's the data set that the model uses to train itself. But then the 30% that you hold back, you then use to actually test the model. So again, because it's got the answers in it, it means that the model can then run that new data set against the new model that's created, and then look at the answers that it predicted versus the actual answers to see whether the model is actually accurate or not. If it is, if you're happy with that model, you then create the model, and then that model will then sit there and allow you to push new data into it. So in our fraud transactions example, you'd be putting new data through that obviously you don't know if they're fraudulent or not, and then the model will then make a prediction for you. Now you can do that in batch. So if you've got a large file that you want to actually run predictions across, you can do that. But what's becoming more common is that you actually want that predictive model to run in near real time. So you actually have near real-time data coming in. So again, in our transaction type of example, as someone actually ran their credit card through the machine, that would then send that off in near real time. The model would then very quickly tell you whether it predicted that that was a fraudulent transaction or not. So the prediction would pop out the back. And that's a fairly generic type of machine learning type of pipeline. Now what I wanted to overlay on this for you was the different Spark components that might be involved in this. So typically we see that this initial data preparation step is often served really well by Spark SQL. So with Spark SQL, as I said before, you can transform the data, you can cleanse it, you can make sure that you've got the fields that you need and not the ones that you don't. You can potentially split fields up if you need to, coalesce them together, whatever makes sense for your model. Then the actual splitting of the data, the training, the testing, and then the creation of the model, and also the predictions themselves are going to be done by Spark ML or MLlib. And so those libraries sit in there to help you to do that. And then if you're going to be pushing near real-time data through, then that's where Spark Streaming can help you do that. And so I think this is a really great example of one of the attractions of Spark is that each of these components, you could do them in other technologies, but the attraction of Spark is that you can do them all in one place. And so one of the things that a lot of data scientists have an issue with is that they spend a lot of their time preparing data or moving data between different systems rather than actually doing what they really want to be doing, which is actually training and testing their models. And so within Spark, this makes their job much, much easier. So you can stay within the Spark cluster, you can use Spark SQL to prep your data, Spark ML to create your models, and then Spark Streaming to push your new data through that model. So a great example of the power of Spark. Now, one of the lesser known modules of Spark, and probably because it's really still in its infancy, but I wanted to mention it here just for completeness, is GraphX. Now, GraphX is a graph processing engine that can help you to analyze the relationships between entities. So if you think about a typical graph, and now these entities could be people, they could be places, they could be nodes on a network. Anything that's got relationships between them can then be modeled into a graph. And graph databases and graph processing engines have become very popular recently to deal with a whole bunch of types of processing that are slightly more difficult to do with relational technologies. Now, there's a little bit of a nuance in the graphing world here, which I think often gets glossed over, and that is that very similar to the way that we look at SQL databases, there's also that kind of split in graph technologies as well. So if you think about the SQL world, you've got your transaction databases, so your MySQLs and your Postgres engines, etc. And then you've got your databases that are more focused on analytics, so some of the MPP databases like Redshift, for example. And the same is true in the graph world as well. So some of the graph databases that you would have heard about, things like Neo4j and OrientDB, they're typically more focused on transaction processing. So adding nodes to the graph, doing lookups in the graph, etc. And then you have the graph processing engines, and these typically work in more of a batch fashion where you're actually running some analysis across the network. So, how many levels is this particular entity separated from a different entity? Things like that. Things where you have to do a lot of scanning, a lot of hops between the different nodes. And so GraphX falls into that second category. So it's a graph processing engine as opposed to a graph database, like say Neo4j. And so these two technologies typically would work together, where you might use Neo4j to actually be your kind of online transaction graph database that you would use day to day to add nodes and update the network, and then the GraphX processing would then work offline to actually run those deep queries for you. So as I said, early days for GraphX, but I think you'll hear a lot more from that as it matures. So that's the essence of Spark and the different modules that come with Spark. So I wanted to give you a good overview of the different modules there. What I want to do now is just move on to Amazon EMR and talk about that a little bit before we talk about why the two of them are so good together. So if we go back to our original graphic where we're looking at the Hadoop stack, what EMR does for you is, instead of you installing the applications, installing Hadoop, having to provision the underlying hardware and making sure that all of the nodes are talking to each other and that all the right ports are open and everything's installed correctly, that's what EMR will do for you. So if you want to run a Hadoop cluster, you would talk to the EMR console and you would say, I want a cluster of this particular size and I want these applications installed, and then EMR will go away and do that for you. It will talk to EC2, it will provision the instances, it will install everything that needs to be installed, etc. And you can then obviously run all of the other applications that you need to on top. So that's basically what EMR does, and what I wanted to do now is just step through why that's a good thing. So what are some of the things that you get with EMR that you don't get if you're running it yourself? So the first is automation. We'll look at what you get in terms of automation. The ability to decouple, so the ability to decouple your processing layer from your disk layer. We'll look at elasticity, integration with other Amazon engines, the currency of the open source tools that sit on top of EMR, and then obviously also being able to run some of this at quite a low cost. So let's look at automation. So as I said, one of the main reasons that customers like EMR is that a lot of the work involved in setting up a Hadoop cluster is taken care of for them. So a lot of the heavy lifting involved in creating the cluster is done for you. So firstly, obviously there's the provisioning of the infrastructure itself, so provisioning the EC2 instances. EMR will do that. the actual cluster setup, so making sure that everything is installed correctly on those machines, and making sure that each of the nodes is talking to each other correctly. The actual configuration of the Hadoop cluster itself, so there's a bunch of configuration options when you spin up Hadoop that you also have to keep in mind, so EMR will take care of that for you as well. And then obviously there's the installing of all of the applications, so the huge menagerie of different tools and animals and zookeepers and you name it. You can do that through EMR as well. It will then install those tools for you. It will also allow you to then submit jobs at the time that you create the cluster. So the use case we often see there with customers is that they have a very specific task that they want done. So they'll actually spin up a cluster and submit that job at the time that the cluster comes up, and then that cluster will run that job and then it will shut itself down. Very specific tasks, but you can obviously, that can all be automated. And then finally, obviously, monitoring and failure handling. So if one of the nodes falls over for any reason, then EMR will monitor that and make sure that that node comes back up. So that automation component is really key to making running a Hadoop cluster much easier than it has been typically, and allows you to much more quickly get to the business of actually using the cluster itself. So let's look at decoupling. So what do we mean by that? So if we go back to our graphic, one of the issues that a lot of customers ran into when they were running a Hadoop cluster with HDFS as the sole place where they were storing the data was that they then found that they had locked their compute layer with their storage layer. So because both of those layers were sitting eventually on those machines in the cluster, if they needed to add more disk to the cluster, they'd have to add more machines, and those machines would obviously come with extra CPU and extra memory, which they had to pay for but didn't necessarily need. So what we wanted to do with EMR was make sure that customers could use a different external storage layer that was highly durable, highly scalable, low cost, etc., and use that with their Hadoop clusters. So EMR brings with it something called EMRFS, which is EMR's file system. And this allows you to talk to S3 from your Hadoop cluster. And this then allows you to successfully decouple your compute layer from your storage layer. So you can just load data into S3 as you need to. So if you need more disk, you just simply load more data in. There's no need to pre-provision with S3. But you can then keep your cluster the same size. So you're not having to grow the compute on your cluster unnecessarily. Now there's a couple of other really important benefits that come along with that. And the main one is that now that you've got your data in S3 and not locked into the cluster, it means that you can actually start to spin up separate clusters for different tasks. So if you imagine you've got a situation where you've got your data in S3, you might then have a persistent cluster that's running all the time that's allowing people to interactively query the data in S3 either through Spark SQL or Presto or Hive or any of the other interactive query engines. But when you want to run your batch jobs, so maybe your ETL jobs, your transformational jobs, you can actually then spin up a transient cluster. So that doesn't have to run on the persistent cluster. It doesn't have to interfere with the interactive queries that are going on. You simply spin up a cluster, it's completely independent, and then you run that for as many hours as you need, and then you shut it down. And a lot of customers follow this pattern, and it's incredibly powerful because it allows you to really focus on making sure that those clusters are dedicated for certain workloads. And then you might have other workload-specific clusters. And as we say here, they could be different sizes, they could be different versions of some of the tools. So if you've got a dependency on an older version of the tool, that's fine. You spin up a specific cluster for that. And so this gives you incredible flexibility with the way that you start to use Hadoop and all the applications as well. Now, one of the questions that then comes up is, okay, so if I'm using separate clusters, then how do I ensure that tables I create, for example, in my batch job, are then available for people to query with the persistent cluster. Well, this is where you use an external metastore. So one of the things you can do when you spin up a Hadoop cluster is you can specify where the metastore is. And so what's common practice now is to use an external metastore like a MySQL database. And if you're running in Amazon, we recommend that you put that on a RDS so that it's managed by us, and you can make that highly available. So that then as you spin up a cluster, as part of the configuration, you simply say your first job is to then point to the metastore and make sure that you've got access to all of the configuration, all the tables that have been created. And that's how you can share data between different clusters and also different applications as well. Now, one of the other aspects to this then is if you're bringing up different clusters for different workloads, you've then got the ability to be much more focused with the instance types that you're using. So as you know, with EC2, you've got a lot of different families of EC2 machines. We've got general purpose such as the M4s, the M3s, compute, C4s and C3s, and then heavier memory ones, and then obviously instances with more storage. And for those of you who are watching the keynote this morning from reInvent, you would have seen that there's a whole bunch of other additions to this that are coming shortly to make the family even bigger. But the nice thing about this from a big data perspective is that a lot of the types of workloads that we see map to these quite well. So batch processors obviously are pretty unfussy with what they use, but machine learning is very compute intensive, so it loves machines with a lot of compute on them. And then you've got interactive analysis, which is big on memory, and then obviously if you do want to run a large HDFS cluster, you can do that with the bigger storage instances as well. So again, that decoupling gives you that incredible flexibility with being able to have very targeted types of clusters. And then in terms of elasticity, so one of the things that is nice about using EMR is that you can really be very elastic with it as well. So yes, you can spin up the cluster and you can shut it down if you want to, but some customers also want to keep it running, but it is used for different purposes at different times. So you can scale a cluster up if you need to, so you can add nodes to the cluster. You can scale it down again. And a feature that we've recently added, you can actually auto-scale it as well. So similar to what you can do with EC2, so with an EC2 auto-scaling group, you can say, you know, when a certain metric on the machine meets a certain threshold for a specified period of time, then you want an automatic action to happen. You either want to scale that group up or scale it down. And you can do that with EMR now as well. So you can actually say, you know, when the amount of memory on the machines is at a certain level or the CPU is at a certain level for a period of time, then either add or subtract nodes from this cluster. And again, this makes it incredibly flexible and gives customers that kind of very flexible compute power that they haven't previously had with their Hadoop clusters. Now, in terms of integration, obviously we've got close integration with EMR and other AWS services. So let's assume you have an EMR cluster with Spark running. We've talked about EMRFS, so obviously you get very close integration with S3. But you can also connect up Spark streaming to Amazon Kinesis very easily, so that's how you're able to capture your streaming data. You can also connect into Redshift. So Redshift is our petabyte scale MPP SQL Analytics database. So you can use those two in conjunction as well. You can then obviously wrap your cluster with IAM roles so that you can give the roles certain permissions that the cluster can then inherit, but that means you don't specifically need to give those permissions to users themselves. You can shield them behind the roles. And also crucially, you can also then start to use Amazon KMS. So that's our key management service that will allow you to manage your encryption keys if you want to encrypt the data at rest in S3 for EMR to very easily encrypt and decrypt without too much drama. Now, one of the really important things for a lot of customers is making sure that whatever technology they use that's running their Hadoop cluster, it allows them to use the most current of the open source tools. So there's a lot of development and a lot of work going on in the open source community. And so we want to make sure that we can get that into your hands as quickly as possible. And so we've done a lot of work with EMR over the last couple of years to make sure that we can do this. And if you look at some of the dates here, specifically for Spark, you can see that the speed with which we can get those changes and those new updates into your hands is really quite quick. So if you look at Spark 2.02, which is the latest version of Spark, that was released by the open source community on November the 14th, and we got that into EMR, fully supported with EMR within a week of that release. So that really is extremely important for a lot of customers who need to make sure that they can use the latest versions of those tools as they come out. Now, all of these features are well and good, but obviously cost is a factor, and you want to make sure that you can do this in a low-cost manner. So there's a number of ways that you can keep your Hadoop costs as low as possible with EMR. One of them, obviously, we've talked about, which is to use transient clusters, so you're not locked into having a running cluster all the time. You can essentially spin it up and down as need be. But also, if you do have a persistent cluster, you can use reserved instances. So many of you would be familiar with reserved instances on EC2. So that's where you basically say, look, I know I'm going to use this instance for a year or 3 years, and so I'm going to lock that in, and I'm actually then going to pay a much lower hourly rate for that reserved instance. And so once you get to a fairly steady state and you know exactly what you think you're going to be using, you can then use reserved instances to lower your cost. And so a lot of customers use that with EMR as well, and that obviously then reduces the cost of the EC2 instances underneath. Now, the third way that you can save money with EMR is to use spot instances. Now, for those of you not familiar with spot instances, the spot market is a market that we have created for any unused EC2 capacity. We will make available on the spot market. Now, the price of each of the spot instances goes up and down depending on supply and demand for each different instance type, but typically it is a fraction of the cost of the on-demand price. And so what this allows you to do is to then spin up quite large clusters with spot instances and then get through your processing much more quickly. Now, the caveat there obviously is that if the spot price goes up and it goes above what your bid price is, then we may take that instance away from you. So you need to use spot instances with workloads that can tolerate the loss of a node. So we wanted to make sure that EMR could do that. So there's a particular type of node that you can use within EMR that is perfect for use with the spot market. So if we do take the instance away, the cluster will keep running, you won't lose any data, but whatever job that instance was doing, Hadoop will just reassign that to a different node within the cluster. And so this was really important to us to make sure that customers could use the spot market as much as possible. And just to give you an example of some of the savings there, so if you look at a fairly standard machine, an M3 2 extra large in the Sydney region, the on-demand price for that is 75 cents. And the spot price, it does vary, but when I just checked then, it's hovering around 9 cents. So that you can see that you can have enormous savings there if you're able to use spot in your workload. So let's talk about marriage. Let's talk about the marriage between Spark and EMR. So as you can see, Spark gives you a lot of that really rich out-of-the-box functionality, and what EMR brings to the table is the ability to control that cluster, to be flexible in the way you spin it up and spin it down to make it as cost-effective as possible. And so these two together really work very well together. So I wanted to just give you a couple of examples of what our customers are doing. So if you look at Yelp, for example, so they're a recommendations site in the US. They do a lot of machine learning and ad targeting using Spark and EMR. Hearst, a publishing organization, they publish an enormous number of web properties around the world. They use it for their web analytics. Washington Post, again, ad targeting and recommendations. You can see organizations using it for security event streaming. So CrowdStrike, for example, on the bottom left, use it for looking at security event anomalies, revenue forecasting, predictive marketing, you name it. So there's a huge variance in the applications that people use it for. And just drilling into the Washington Post example, I wanted to show you this because it kind of talks to what we were talking about before, where a lot of customers use multiple different clusters. So Washington Post, they look at the number of clicks, the number of videos that people look at, any kind of interaction, and they've got MLlib there running some kind of machine learning algorithm that's segmenting their customer base, which they then look to map users to specific ads. But they also have a recommendation cluster as well that you can see down the bottom there as well, where they're recommending particular content to users. Similarly, if you look at what GumGum do, again, you can see this is a classic use case where they've got a 24/7 Spark cluster up the top there. So that's a persistent cluster that's running all the time, that's constantly ingesting ad impressions and clicks. And from that, they typically do their revenue forecasting and have an interactive dashboard. And then they've got a batch Spark cluster underneath that, which is looking at the clickstream logs. So that's not online and on all the time, but they use that in a very batch-specific fashion. They then process a lot of that data that ends up in Redshift. And then down at the bottom there, you can see they've got a whole bunch of other different clusters that they run for different workloads, typically for for data exploration and testing, etc. So again, just a great example of a customer who is using a number of different very specific clusters, some persistent, some transient. So I wanted to leave you with that thought so that you can think about the marriage of two fantastic technologies together, and you can see how, from what we've talked about, all the goodies that you get from Spark, and then obviously the underlying infrastructure that you get with EMR. So I wanted to leave you with that. I also wanted to just point you to the details page on the website, which talks specifically about EMR and Spark. So if you follow that link, that'll give you more use cases and more details, etc. And I also wanted to mention the AWS Tech Chat podcast, which I run with one of my colleagues. So this is a great way to get a roundup of all the latest AWS updates and news, etc. And we'll be having a couple of reInvent specific shows coming up in December to help you wade through the enormous number of announcements that's happened this week. So you can download that from iTunes or SoundCloud, or if you follow that bit.ly link there, that will also take you to the landing page where you can sign up as well. So it's not just big data content; it's across all the AWS services. Although I don't tell my co-host this, but I try and sneak as much big data content in as I possibly can. So that was it from the presentation I wanted to give you. If there's any questions, please send them through on the chat window, and we'll try and get through them as quick as we can.